Hello, 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 hello. Hello. Okay, good afternoon, everyone, or good evening, everyone, or good night, everyone, wherever you are from. I hope you are able to hear me. I can see a few people already joining. So if you are able to hear me, can you just type a message in the chat box so I know that you are okay, and then we will start. Okay, that's great. So I think without wasting any time, I would like to welcome you all. This is the first time I'm going live on YouTube. So if there are any glitches or hiccups, then I apologize at the start. So in today's session, it's gonna be not that long. I will just gonna go through a simple Uniaxial test simulation example, which was asked by one of the subscriber. And then if you have any specific questions, then I will try to answer them as well. So you can feel free to ask your questions in the chat box, or if you want me to slow down as well, so I will slow down too. So let's get going, and I'm going to bring the abacus on the screen now. So I hope you can see the abacus software now. And I think there is a delay, so I will always see it later on. So I hope you are able to see the screen. Okay, so in this example, what I'm going to do, I'm going to create a uniaxial test, which is a kind of a representative of a uniaxial test. And this will be a one element model. And this is generally used to identify material parameters. I already have a video on that, but one of the subscriber asked that if I can actually show how I can make the model and how I can really justify my boundary conditions and loading, etc. So let's say if we have a Uniaxial test which is being done using a displacement control test, for example, then how to create a model which can then be used to identify material parameters, as I have shown you in many of my videos. So I'm going to first start with the part module, and I will create a part. I will call it, let's say, Uniaxial example, and I will go with an extrusion option because I want to keep everything 3D, and I will press continue. And now I will create a square which will be, let's say, 1 from a 1. Again, Abacus doesn't have any units, so as I always say, that always define your own unit, so you are responsible for the unit. So if the geometry you are making is in millimeters, then everything should be in millinewtons and millimeters and megapascals if they are stresses. So this is what I have created now, and then I will press cross, I will press done, and then it will ask me for the extrusion. So again, the depth also is 1, so I will get kind of a cube here. And then I will go to the next module, which is the property module, and in this case I will have to define the material properties. So for that I will create a new material, let's say again Uniaxial material. If it's a dynamic analysis, you might have to define the density, so you have to go to general and define density. If it's a static analysis, then you can live with only mechanical properties. So I will first define the elastic property. So if I assume it to be a metallic material, then I can live with the isotropic properties. If it's a composite, then I can define laminar, orthotropic, and isotropic material properties as well, depending on the material type that you're having. So in this case, I'm assuming everything is in millimeters. So this will be 210 megapascals. So I'm just assuming it to be steel. And I'm again defining the Poisson's ratio as 0.33. If it's an elastic plastic material, and I need to define the plastic part of the curve as well, so I can take it from the experiments, or I can use different types of models which are available as well. So let's say if I assume plastic, then I can have isotropic hardening, I can have Johnson and Cook parameters. So again, I have a very detailed video on this, how to identify parameters for Johnson and Cook model, both using Abacus as well as using the Excel as well, because again, that's that one integration point solution. So again, it depends on you what you really want to do. I will just create, for simplicity, I'm going to use something which we already know. So let's say yield stress I know as 450 or something megapascals at 0 plastic strain, and then I'm assuming it to be, let's say, a linear hardening in the stress strain range. So I will just give a value. Again, these are just fictitious value I'm using. So now I have defined the elastic plastic material. If we already know it's a complex material, then you can use any of these models which require material parameters, and you have to identify those through experiments. Right. So once we have done that, then we go and create a solid section where we select we can again call it Uniaxial or steel or whatever section. And it's a solid because everything is solid in this case, and homogeneous. This means material properties are same throughout the sample or specimen. So once I have done that, I will select the material type and I press OK. And now I will assign this section to this material. Once I do that, it turns green, as you see, and this means your material properties are correctly assigned to this component. Then I go to the assembly module, and in this case, I will first instance the assembly here or component here. So if you have multiple components, you have to do it one by one, or you have to, if it's in this case, it's only one, so you can just bring that component here. So you have to press instance part, and then you select the components which you want to really bring in, and then you press OK, and then your part is in the assembly module. If you have multiple parts, then again, I have videos where you have to rearrange your components. And for that, you need to apply different types of operations like translation, rotations, alignments, etc. So again, I have a lot of videos on my channel on that as well. Once we have done that, so we go to the step module where we have different options to define the step. If it's a quasi-static analysis, then we can use static general analysis or a step. If we have a dynamic analysis, then we can go with a dynamic explicit as well. So in this case, again, we will keep our life simple and we go with a static general analysis. I will define it as a nonlinear geometric, because if we have a very large deformation, then it's always good to activate this. If it's a small deformation problem, then you can live without it as well. For the maximum number of outputs, I always suggest to use the larger values, because if the number of increments go beyond 100, then it will stop. So if we give a larger value, so we basically avoid that stoppage, and then we have to restart it. So, and also this is the initial time increment. So I say, okay, start with 0.1, and the maximum I also keep it 0.1. So from 0 to 1 second, it will have almost 10 increments, and I will get the output for 10 increments as well as a default. If I want to change the frequency of the output, then I have to go to the second option in the step module, and I can edit and I can change how many outputs you need. So in this case, every increment, it gives you one output. So we will have 10 increments and we will have 10 outputs. And again, we can change the variables as well. If we have contact, if we have failure criteria, so we can enable those as well. So once we have done that, we go to interaction. We don't have any interactions here because this is only one component. If you have multiple components, then you can define contacts as well. Then we go to the load module. And in this case, I'm going to use the displacement control test. So what I'm going to do is, in the case of uniaxial test, you need to fix 3 of the planes orthogonal to the plane. And then you have to keep 2 of the surfaces free. And on one of the surface, you apply the displacement boundary condition. So I'm going to apply the displacement boundary condition, let's say on this surface first, which is in Z direction, as you see. And I will fix it in Z direction, which is U3, right? So this can move in any other direction, but except for the Z direction. Similarly, this one, we will fix in X direction. So now I'm going to do that now. The displacement boundary condition, select the surface, and then I will fix U1 for this component here. And similarly, I'm going to do the same for the top one. I can do the bottom or top, it's your call. So if I do this, I will select this, and this, in this case, I will fix it in Y direction. So I will select U2 to be 0. So now we have firstly constrained the component as required. And if we go on the other side, so we have 3 free surfaces. So on one of the 3 surfaces, we can apply the uniaxial loading. So that's what I'm going to do. And I think I will go in the Z direction. So I'm going to apply boundary condition in Z direction here. So again, it's your call what you want to do from that. So I will apply this. And let's say if I apply a displacement of U3, because it's in the U3 direction, and let's say a value is around -1. And ramp means it will increase linearly, but you can apply your own displacement. If you know the displacement from the test, that how it was changing with time, you can basically create an amplitude function and you can assign that as well. In this case, we're going to say that it's going to start from 0 and it will go up to -1 with a linear increment. And we are giving it -1 because it's going in the negative Z direction. So that's what I have done here. So now if I click on this isometric view, then you can see this surface is fixed in Y direction, this one in X direction, and this one in Z direction. This face on the other side is pulled in Z direction with a displacement boundary condition, while this surface and this surface is free, which we want to be free, which is equivalent to the uniaxial test. So what will happen when you pull the sample in this direction? So these surfaces are free. So they will start to have this contraction, which is the Poisson's effect or stress-free state, as you'll see in the uniaxial test. And that's why we use these boundary conditions to replicate or represent the uniaxial testing in the material. So once we have done that, we go to the next module, which is the mesh module. And in the case of the mesh module, what we're going to do, we're going to create one single element, because we are just replicating or representing the whole uniaxial test with one element, right? Because we are trying to replicate the material behavior. So since we already know what is the size of this thing, so I will assign a global seed. And since the size of each side is 1 millimeter, so I have used that here as well. And once I have done that, I will just press the mesh part and press yes. And now I have my part has been meshed. So everything is ready now. Meshing, loading, boundary conditions. So we start from the part, we define the material properties, we assign the material properties to this part, we assemble the parts together, we define the step depending on the type of analysis. Then we define the loads and boundary conditions, mash it, and then we go to the job module and we start creating the job. So again, I will call it Uniaxial, right? And we press OK. So once we have done that, normally I always go to the precision section of the job and I always select full. If you have very large or very small number, it should take into account all those as well. But again, depending on the analysis, you can change. You can use parallel simulations if you have many elements, or if your simulation requires a lot of time. So you can use multiple processors as well. You can also allocate memory as well. Currently, it can use up to 90% of the memory in the system. So I'm going to keep everything default, just full analysis I will select. I will press OK, and that's pretty much it, what I have done. And now I will press the submit button here. So once we have submitted, it says submitted, and we can check the status of the job by pressing the monitoring button. And as you can see, it will show what is happening in real time to our job. So you can see it finished in no time because it's a one element model. So it will go fast. There are no errors. There are warnings. And these warnings is basically, for example, in this case, the strain has exceeded 50 times the strain cost. So this means my boundary condition, which I have applied of 1 millimeter, is too big for it, since my time increment is this. So again, you can go back or change the mesh size, or also change the boundary conditions as you require in your actual test. But in this case, we are just demonstrating, so it should be okay, hopefully. Once we have finished, then we go to the results and we see the results, and you can see that it started from here. We pull it and it contracts. So you see the Poisson's effect as it starts to contract in the lateral directions, and you are pulling in this direction. So once you see everything is working fine and you don't see any anomaly in your model, then what you can do, you can basically plot the stress strain curve, because ultimately you have to compare the stress strain curve which you get from here with your experimental data, right? So you go to the XY data manager, and then you press create, and then you say, okay, from field output, I need XY data. And here you can decide which stresses you want. So since you are pulling in Z direction, so I can use measles stress, or I can say plot S33, and also the logarithmic strains or strains in 3 direction as well. There is only one element, so we can give a label as 1, or we can just select directly from the viewport as well, as I have done here. And now if I say save, so I can just see that stress and strain as a function of time are being saved. So if I plot any one of them, let's say stress, then you can see, since I have given a bilinear function, this is the elastic part, then yield stress is around 480 I gave, and then I have a linear hardening as well, because I only gave 2 values in the plastic part of the material data. So I get a bilinear stress strain response, and it's as a function of time. And now if I ask you, what do you expect in strain? How would the plot look like? Anybody can say something on that? Is it going to look the same as the stress, or will it be different? Before I plot. So meanwhile, I wait for it because I know there's a delay. So I keep on talking as well. But any ideas, how would the strain plot look like? Would it look like the same as this in terms of time, or would it be different? Anyone there? Yep, it would be different, definitely. And the difference would be based on the boundary conditions, because the strain will follow the same path as the displacement boundary condition which we have provided. And if you remember, the displacement we assigned was from 0 to -1 and in a ramp fashion. So it will be a linear one. So if I plot this now as a function of time, it should show a linear curve, linear or straight line, as you see here. So that's correct. Now so both are now in terms of time, but I want to plot stress versus strain. So what I can do, I can go to create, operate on XY data, and then I will say combine option here. And then I will say plot strain and stresses as vertical axis. And then I save it as, let's say, stress versus strain. And then I press OK. And now I go and plot this stress strain curve. So now you have a stress as a function of a strain, and you can see how the stress increases as a strain keep on increasing up to 0.7 in this case. So this is how you can do a uniaxial test. Now what you can do is, if you have experimental stress strain data, you can go back to the XY data manager. You can create, and you can either read a file and import it here, or you can also select keyboard. And if you have an Excel file, you can copy paste your data here as well, and then tell the software that what is on X and what is on Y. And then once you have done that, you can actually plot both the curves together and then see how much is the difference. And then you can play around with the parameters or properties to reach to the final values. Okay, so next is basically, so this is how you basically do a uniaxial simulation, and you can run your simulation this way. So any questions until now, or you guys are good? Or anything else you have, not about this, but anything else about Abacus, or any problem you're facing, you can type in the chat. And if it's a shorter question, I can show you now. Otherwise, I can reply or make a separate video as well. So feel free to type, as I said before. Anything else you can do, you can create nice animations as well. So let's say if this is a quasi static, you have to plot every time. If you want to make an animation, you click on this, and then you can basically see it's very fast. So you can go to the options here, and you can say play once. You can slow it down, apply, and then you see it goes slow. You can scale it down. There are so many parameters here. You can skip some of the increments as well. So you can do a lot of stuff here. So if you want to save this animation, if you're happy, then you can go and say animate and then save as. And once you click on this, then you can save it as AVI file, and that you can then take it to your website, your presentation, or animation file as well, as I show you in many of my PowerPoints before the start of the videos. Okay, so this is about animation. If you want to change a variable, let's say you want to see how much plastic strain is there, equivalent plastic strain, then you can go and play with that. So this is the equivalent plastic strain. And what you would see, it starts to from zero because initially it's elastic, and then after the yielding, you will see the equivalent plastic strain, which is happening in your structure as well. Similarly, if you want to see displacements, then you can plot those. U3 is more important here because U3 is the one which we are applying up to -1 here. Similarly, if you want to see the individual components of plastic strains, and you can see that as well from the model, and you can plot those as well. So yes, you can do a lot of things with this for post-processing. If you want to take this as an image, then again, you can bring this on the screen. You go to File, Print, and then you select from here the file option. Then you can select different options with different formats you can have. I normally go with PNG, and I can basically go with the best quality, or you can change this as well, resolution as well. And then you can save it as a file as well. So just give it a name, and then it will save it for you, as you see at the bottom. So this is what I wanted to show you here. So if you have any questions, I am happy to answer now. Otherwise, this was just a short session for you And if you want to see anything specific in the next live session, then again, you can send me an email through my website, which is www.professor3mac.com, or you can just comment on below my videos, and I will definitely come back with some of those in the live session. Okay, so there is a question from one of the audiences. I have my experimental stress strain curve, but how can I add the load condition of the real situation to try to catch the experimental curve? Thanks. Okay, so if you have a real stress strain curve, so as I told you before, you need to first go and apply the boundary conditions as you do in the experiment. This is the first thing which you have to ensure. So what you will have to do in this case, we just said, okay, total strain or total displacement is -1. In your case, it will be some final value. And if I can bring the Excel on, then it will be easier to see. So let's say your data was something like this. So 0.1, 2, 0.3, 4, 6, 0.7, 8, 0.9, then maybe 0.995, then 1.0, and so on. So let's say this was your stress, and this was 0, and then maybe 200, 300, 480, 50, 500, 700. I'm just giving some random values here. 850, 900, 950, 1000, and then 1050. So this is your condition. So this should be your boundary condition. Your loading condition, the boundary condition should be matching this if you have a displacement control test. If you have a force control test, then in that case you may have or let's say this is, I will just keep it like this. So let's say this is displacement U and this is the force F, right? So with force, again, if you are doing an experiment, you can convert this force, dividing it by the actual or initial area, you will get a nominal stresses. And if you divide by the actual true stress, then true area, then you will get the true stresses. So again, depending on your definition, you can compute the stresses, which will be equal to force over the area. The software generally give you that in the post-processing. So if you have this data and you think your test is displacement control, then you should apply the displacement using this kind of increment. So if I were you, I would just copy this. And let's say if I have another column here, oops, sorry. If I have another column here, and that is time. So let's say time started from 0, and then it went up to 2.5, 1, and so on. Something like this. The time looks something like this. Okay. So this will give us my amplitude function. So if I go back here, so I have to just apply the loading conditions as I have seen, or as I have done in the experiment. So I will go with the amplitude. So instead of defining a linear function, I will go and give a tabular values where I will give the value of the time and also the amplitude. So I already copied that from Excel from here. So I will just press Control C. I go back to Abacus and I will paste it here. So now my amplitude will be the same for displacements as it was in the actual test. And then I can select that amplitude here. So now my loading conditions will be the actual real situation. Once I have done that, and I have ensured that my loading and boundary conditions are very much the same as the experiments, then I will do and repeat the same simulation, go to the results, and then plot the results as I did it before here. And then I will compare this with the experimental data. So let's say if my experimental data was, again, if I say that displacements and 0, 0.1, and so on. Let's say this is my test data at 0. Let's say 485, 500, 600, 700, 800, 1000, 1050, 100, and 1200. So let's say this is my experimental stress and strain. So I call it a strain, and this is stress, right? So I will just take this data, and as I told you before, you can create the data from your keyboard. So you just copy and paste the data, which is experimental data. Tell what is in the X column. In that case, if you remember, it was a strain. So I will select it to be strain. And here, y-axis is the stress. Units should be the same. Make sure all the units are consistent. And I will select a stress. So X is strain, Y is stress. I will plot that and show you how it looks like. Again, I have just made a fictitious data, so ignore it. And I will save it as experiments. Yeah. So I have now experimental data here, which is, if I plot, it looks something like this. And this is my first simulation, which I did. So now once I have done the simulation, I can remove this time function here and I can compare it with the experiments. And then I will see how good it is matching with the experimental data. If it is too different, then I will have to go back in the materials module here and I have to change the material properties, whether it is a plastic part or I have to use a different model. If I'm using Johnson & Cook, then I have to change and play around with the parameters and then rerun it again and then compare it again so that I get the best of the comparison between the two. And once I have done that and all the curves are matching, then those are the that will be the validated material model for that specific experiments which you are doing. I hope this was the question you were asking. So this way you have to keep on doing it unless you get a good fit. I already have a detailed video on my channel, and if you have a look at that, then definitely that would help you out as well. I can post the link in the description as well. Let me find it out. So YouTube, I go here and by the way, I have another channel which it discusses about all the scholarships as well. So if you are really interested in doing or looking for scholarships for higher studies around the world, then do follow that channel. I post a lot of stuff there about scholarships. These are just short videos. So if you search on my channel here, the videos, and then search for material, then so this is one of the video here. So if you, I'm not gonna run it again, but I will just share the link in case if you want it. So here is the link. And with respect to that one, if you search for other material models, and I have done it for others as well. So I hope you will find it useful. So I hope you guys find today's session useful. And if in the future you want any other thing which you want me to learn or you want me to go through, then please comment below or send me an email. I will create these kind of live sessions to answer your questions. So if you have any question, then obviously type here now. I still have a few minutes. Otherwise, I will say goodbye in next few minutes, and I will see you most probably with the next live session very soon. Okay, then thank you very much everyone for attending. And there are quite a few people here. At least I can see 4 people who are joining. So it's a good sign. It's a good start. So hopefully I will see you in future videos as well and future live sessions as well. So thank you for joining today and have a great time. And if I can be of any help, then please get in touch and I will try to help you as well. Thank you and bye for now. Enjoy the rest of your day or night and rest of the week as well. Goodbye.